All right, everyone. This is the first lesson of chapter 7, and this lesson is very much conceptual, as much of the chapter is. So, what I have here is I've got the notes are already kind of all filled out, and I'm just going to talk through the notes because that's really what it's all about today. Um, so this lesson is about a lot of vocab, and you can see here on the top, this is all vocab. So let me try to give an example to this. We're going to get into, you can see here, what is the average for the chapter 6 test. That'll be down here. But here at the top, let me give you another context. Like, why do we do statistics? Let's say I want to know what is the average screen time for teenagers, for teens. Okay, it's a good statistical question. Um, I can't very well go ask every teenager, say every teenager in the country. Can't do it. The the teenagers in the country are the population, okay? And I want to know the average for all of them. So that is called a parameter. That is the true value for all the teenagers, the entire population. Um, I highlighted the P's to help you remember that. Parameter is describing a population. Or you can think of it this way, populations produce parameters. Lots of P's in that sentence. P, P, P. But I can't very well go ask the entire population. Very hard to do. So what do? We collect statistics, which are simply values that we get from a sample. So look again, statistics and samples both start with the letter S. So that maybe helps you with that. So I could go ask a sample of teenagers and get a statistic, and samples produce those statistics. So in this table, it's showing you on the left, these are the symbols that we use for statistics. And on the right, these are the symbols that we use for parameters. And you should start using them very carefully and correctly. So for example, I'll show you these first two. We've been seeing these a lot. Where do you see these? X bar and S sub X. They come from samples. We have seen them on the TI-84. So I go to stat and then edit. I made up a make-believe sample. Like pretend I asked 7 teenagers, take out your phones and check your screen time. So there you go, 4 hours, 6 hours, and so on. That's a sample, and this sample can be used to go stat, calculate, and get the one variable stats or one variable statistics, like this. And there they are. There's your X bar, you can see it, and there's your S sub X. Q1 and Q3, you can see all that. Those are all statistics. Excuse me. Because where did they come from? They came from this sample of 7 teenagers. A p hat, we'll get into this in later lessons. A p is a proportion. When you put a hat on top of something, it means predicted. So it is the predicted proportion that we get from a sample. An example would be, what is my free throw percentage? So I could go down to the gym, I could shoot 50 free throws, and I could get a predicted proportion based on how many free throws I make. In the Barbie lesson, we predicted how far Barbie would fall, so we were doing Y. Y with a little hat. We call it Y hat or P hat. So these, notice they don't really have anything above them. They don't have bars or hats. They're just kind of by themselves. These are the symbols that we use to talk about the entire population. So what is the average screen time for teens? That would be a mu. If I could ask every kid, that would be a census. If I could, I would have mu. but I can't. I asked 7 kids. So what I have is an X bar. What I have is a statistic. So there you go. Just write those down, memorize those. So today we're going to be taking samples from a population. Then we will use the average from that sample to estimate the average for the population, kind of like I just talked about with the screen time. We're going to do this for two examples. First one here is about a very small school. There's only 5 kids in the school. We're making this very small so we can wrap our minds around it. They all took the Chapter 6 test, and they got these scores. One kid got a 60, a 70, an 80, and another got a 90, and another got 100. Only 5 kids. So what is the mean or the average of those 5 scores? You could add them up and divide by 5, but the 70 and the 90 are balanced around the 80, and the 60 and the 100 are balanced around the 80. So the average is going to be 80. Now, remember, this is the entire school. That's all 5 kids. So that is why I'm using this symbol, because it's the entire population. Okay? And that's why I'm calling it a parameter. This value came from the whole population, starts with a P. So this is a parameter, starts with a P. Okay. So let's pretend this was a much bigger school. And the only way I could figure out the average was to sample some of the kids. So what is 5C2? Bear with me here. There's a reason I'm asking you. On Desmos, you go 5, math, probability. There it is. We'll come back to the screen in a minute. We're going to do number 5 as well. We'll do NCR, 5C2, and that's 10. Why do we do that? We now know that I can take 5, choose 2. There's 5 kids, and I'm trying to take different samples of size 2 from the population, okay? So if I have 5, choose 2, and I now know that's 10, there are 10 different samples to be different possible samples to be collected. In class, we took time to find all of them, write them all down. So it's somewhat formulaic. You see, these all have a 60. So I matched up the 60, 60 with 70, 60 with 80, 60 with 90, 60 with 100, and there's 4 of those. Then I took the 70. The 70 was already matched up with the 60. So then I just did 70, 80, 70, 90, 70, 100. And so I had 4 here, 3 here, and you can kind of see there's only 2. Oops, I put an 85 there. That's a mistake. Only 2 with the 80. And then lastly, 1 with the 90 right here. So 4 plus 3 plus 2 plus 1 is 10. So I actually listed out every single sample. And what are the arrows pointing at? All of these are X bars. This is an X bar, this is an X bar. They're all X bars. It's simply the average, the mean of these two, right? Where's the middle of 60 and 70? Well, 65. Where's the mean of 70 and 100? Add them up and divide by 2, and you get 85. Okay, so all of these, maybe I'll highlight them in red. These are all statistics, right? In red. They are the result of samples, okay? And then we can take them all and make a dot plot out of them. So the 65 is right there. The 70 is there. 75 is there. There's another 75 right there. That's why I have 2 and so forth. There's 10 dots here. There we go. What we have just created is our first sampling distribution, also known as AKA, just say it backwards. It is a distribution of all the samples, right? Which makes sense. So in this case, there's only 10 samples. The textbook definition is What is this? It is the value of the statistic for all 10 possible samples, right? We had 10. All 10 possible samples of size n. So in this case, what size did we have? We had size 2, right? We were just taking size 2 from the population. So this shows all the different results you could get when you take a sample of 2 kids from a population of 5 kids. And it gives us a pretty good idea of the true value, way up here, of the parameter. Sorry, I got a bit of a scratchy throat. The parameter is located right in the middle, right here, right in the middle, which is good. In other words, the sampling distribution is centered at the parameter, which is good. I would look at this, and if I had to guess what the parameter was, I'd say, well, I'm going with 80 because it's in the middle. Okay, now let's just scale this up a bit. This was only a school of 5 kids. Not very realistic, right? What if you want to know the average screen for all the teenagers in the country? Much harder question. So let's scale it up to a school where there's 40 kids who took the Chapter 6 test, okay? So this 40 kids who took the test, moving forward, this is my population, okay? 40 kids. And I'm going to randomly sample 5. Randomly sample 5 of them. And I'm going to do that to try to figure out the average of all of them. That's why we do statistics, right? We take samples to try to figure out the true value for everybody. So 40C5 is the total number of samples of 5 kids. It's a massive number. You can do it on the calculator, right? Just a quick refresh. 40 math probability C5. Boom. That's a big number. Meaning there's a lot of different samples to be had. Okay? We are not going to do that many. What we're going to do is have each of you right now just do one. Each of you is going to take a random sample of 5 of these kids. You can see here I did this and I got these 5 numbers. But how did I really truly make it random? This is a good reminder. How did I get the 93 and the 91 and the 84 and the 86 and the 86, right? I used, excuse me, sorry, the random integer button. It's right next to the C button here. Math probability number 5 right there. And you just go 1 through 40 and comma 5. This will give you random groups of 5 between 1 and 40. Oh, look, the first one here has a repeat. It has 232, so I'm going to go again. So then I would, if this was mine, I would say, oh, okay, the first kid is kid number 8, right? And that would be, the score is 71. The next kid is kid 14, and their score is 81. And then kid 31 is a 93. Kid 12 is a 70. Kid 23 is a 67. So with those random numbers, I would have those 5 red circles. Those would be my 5 scores. But I already had my sample here. Let me get my average. 93 plus 91 plus blah, blah, blah. And then divide by 5. So my average of those 5 scores is 88. Ooh, I'm going to just do this too. This is an X bar. And just a quick reminder, what does that mean that it's an X bar? Go way back up to the top. If it's an X bar, that means it is a statistic because samples produce statistics. Okay, now if you're watching the video, you're probably gone. That's fine. What we did is every kid came to the board all day long and put their dot up here. So here's my dot, 88. I would have put my dot like right here. This was all 4 of my classes, so it's a lot of dots. Okay, you can see way over here on the right, I think this is a 92. There were quite a few kids here that got an average of 92. But you can also see kids got low averages in the mid to low 70s. Okay, so this is our class-wide effort to make another sampling distribution, another distribution of all the samples. Now, we're not going to get anywhere near this number. That would be insane, but it gives us a pretty decent picture. Okay, um, so at this point, I'm going to reveal what is the mean score mu of the population. Remember, that's the symbol for population. So I'm not going to make you add all these up and divide by 40. Bada bing, bada boom, the answer is 82.1. Okay, so my sample was too high. That happens. Sometimes samples are too low. That happens. What we did, we took time in class. I counted up all these dots. We had 103 samples, which means the median is the 52nd dot, which I counted and got carefully to that dot, which is at a value of 83. Okay, so remember up here, the distribution was centered at the parameter, which is good. All right, so down here, this is the center, or I'll put a line down it. This red line represents the center. So if I had to use all of my class's samples to make a prediction for the average of all 40 kids, I would say, I think it's 83. Because what I've done there is I'm saying, okay, 83 is the middle, so that means all of these are underestimating the truth. And then all of these, these are all overestimating the truth. But that's to be expected. Some samples are going to be too high and some are going to be too low. But the middle is going to point you to mu. It's going to point you to the parameter. Um, so number 8, I kind of went out of order. Estimate the center of our dot plot, which I already did. So look how close we got. We took 103 samples and we got pretty darn close. I feel pretty good about that. So last idea. This sampling method worked out pretty well. It was centered in pretty much the right spot, and half the dots were too low, half the dots were too high. What I'm getting at is that it was unbiased. This is an unbiased sampling distribution because it is centered at the mean of 8, well, pretty close. In other words, it is centered at the parameter, okay? Um, I'll add one more thing. A biased method will consistently over or underestimate the parameter. And remember, the parameter is the truth. But this one was not biased because it wasn't doing this. Yeah, about half the time it was too high and half the time it was too low. So we're okay in that regard. There are no quick notes because I've scattered them throughout the notes. Thanks for watching.